In this video, we are going to talk about the inverse Park transformation, which purpose is to transform the direct and quadrature voltage reference values from the rotational reference frame to the stationary two-phase XY coordinate system by utilizing the measured electric angle of the rotor pole flux. As you may know, the direct and quadrature quantities are fictive mathematical representations created for an easier control behavior of the measured currents using PI controllers. Because of this, we shall transform these reference voltages back to the three-phase coordinate system where the inverter can realize them with PWM technique. In the next slide, we are going to deduct the mathematical representation of the inverse Park transformation. Afterwards, we will be able to implement the necessary scalar equations with ease in Simulink environment. Let's get started. Currently, you can see the matrix operation for the inverse Park transformation. Fortunately, the connection between the direct and inverse algorithm is pretty straightforward. We only have to take the transpose of the direct Park transformation matrix to obtain the inverse version of it. The transpose operation in our case will mean that we shall mirror the elements in the matrix by reference to the main diagonal of it. This will result in an exchange of places between the minus sign and positive sign functions with the arguments of the theta electric angle of the rotor. Note that here we are dealing with voltage dimensions, however, the general mathematical operation can be applied to arbitrary physical quantities as well. You can see the dq and xy coordinate systems on the picture. The theta electric angle is constantly changing due to the fact that the dq coordinate system is rotating with the PMSM machine. The green vector represents the resulting reference voltage vector that we would like to realize in the stator of the electric rotary machine. This vector can be described in both aforementioned coordinate systems as well. The necessary scalar equations for both x and y directions can be expressed by using the row-column multiplication technique from the matrix equations on the slide.